Okay, so we're going to be looking at the sort of numeric interpretation or numerical interpretation of vectors, just to get you into the swing of things. This doesn't necessarily need vectors to solve, but have a think about it and see if you can come up with the answer. Pause it now and give it a go. Okay, so what did we come up with? The answer should be, did we get it? It's the square root of 2. So just as an idea of this, imagine you've kind of got a piece of paper with a grid on it. I appreciate we haven't got that here, but we go east once, twice, 3 times, 3 kilometers, north twice, west twice, and south once. And hopefully just with a bit of visual inspection you can see that you've kind of got this box, this 1 by 1 box. The blue dot is where you've ended, red is where you started. How far are you? You're that far, right? And how far is that? Well, if that's length 1 and if that's length 1, then a bit of Pythagoras, 1 squared plus 1 squared is 2, square rooted, and you've got square root of 2. Okay. Right, so let's get on to the vector stuff. So we actually already did this. We did multiplying vectors by scalars and we did adding vectors, but we did it in a geometric sense. So just to remind you, multiplying vectors by scalars means you've got a vector and you multiply it by a number. It either gets longer or it gets shorter, but the direction stays the same, right? So it's getting longer, it's getting shorter. That's what multiplying a vector by scalar is geometrically. When you add vectors, that's you, if you can see me in the little screen, this pen is one vector, let's say, and then the other vector is being added to the end of it, and any other subsequent vector is added to the end of it. You add them head to tail. So that's the geometric interpretation of adding vectors. The tail of the vector gets added to the head of the previous vector. We didn't need any numbers to do any of that, to define it that way. But now we're going to define it a bit more properly, or a bit more rigorously, I should say. So easiest way is with an example. Let's make something up. Let's say I've got the vector A and it's 5, 3. Okay, so I've written as a column vector, 2-dimensional, and let's say I have a scalar, let's call it lambda, make something up, let's say 6. Then I could ask the question, what is lambda times A? Okay, and obviously I don't need the times sign, I'll just put them next to each other. So lambda times vector A, or in other words, what is 6 times 5, 3? And it's as intuitive as you think it is. You just multiply every element of the vector by the scalar. So 5 times 6 is 30, 3 times 6 is 18. Okay, another example, let's say I've got a half times the vector 10, 5. That will end up being 10 times a half is 5, 5 times a half is 5 over 2. And I'd write it like this. Okay, as a general rule, let's write here the rule. Lambda times a vector xy, or I don't like xy actually, let's call it AB to make it clear I'm talking about constants, a specific number, some number A, some number B, is lambda A, lambda B as a vector. Okay. And then the other thing is addition. So let me just fast forward and clear this. So we need 2 made up vectors. Let's call them A equals 1, 5, B equals 3, 7. And I say take those 2 vectors, head to tail, add them up. What's the new vector I make? And as it turns out, you could prove this. Don't take it for granted. It can be proven that it's again the intuition you think it is. Take the separate elements and add them together. So I end up with 4, 12. Okay, 1 plus 3 is 4, 5 plus 7 is 12. In terms of a rule, how are we going to do this one? Let's say AB plus CD equals A plus C, B plus D, like this. Okay, and that's my multiplication rule, specifically scalar multiplication, and this is my vector addition. Okay, cool. So that's it, precisely defined. Okay, so then what follows is a whole bunch of examples, 4 or 5 of them, but they're all quite quick ones. So we're just going to blast through a few of these examples, and hopefully any misconception or anything you weren't quite sure about will be cleared up. Obviously, if not, do make sure you ask. But let's just blast through a few of these. A is 2, 6. B is 3 minus 1. What is a third of A? See if you can beat me to it. You can do it in your head. A third of A, that's a third of 2, 6. That is 2/3, 6 over 3, 2/3, 2. That's A done. Part B, that's A plus B. 2, 6 plus 3 minus 1 is 5, 5. That's part B done. C, multiply A by 2 and then take away 3 times B. So the working is going to look like this. 2 times 2, 6, minus 3 times 3 minus 1 equals 2 times 2, 6 is 4, 12. Make sure we don't lose track of the minus. 9. Now 3 times minus 1 is minus 3 equals, sorry I've done this a bit slanted, that's 4 minus 9, 12 minus minus 3, and that there is the final vector. Let's simplify it and just avoid my face slightly. Minus 5, 15. Okay, that's it. And you could even, you don't have to do this, but you could actually simplify that to 5 times minus 1, 3, because you can take the 5 on the outside. But I'm actually going to say now, don't do that as standard. I use the word simplify. I shouldn't have said that, because it's simpler to just keep it as a single vector. So actually forget that, but just be aware that it's possible. Okay, just before we hit our next example, just need to find 2 things. There are some special vectors which are so special we give them a whole letter of the alphabet. So that is the vector I and the vector j, and these are defined as in 2 dimensions, which is what we're going to be sticking with for a bit. 1, 0 and 0, 1. So I looks like that, and j looks like this, and it's a length 1. Okay, remember that within vectors, the first component is the x direction positive, and the second component is the y direction positive. So therefore it should make sense to you that 1, 0 means go right 1, don't go up by anything, and 0, 1 means don't go right or left and go up by 1, which is why this is I and this is j. Okay, and the reason that's useful to define these 2 is because all vectors can be defined in terms of I and j. In other words, if you multiply I and j and add them together in the right way, you can make any other vector. And that should kind of be obvious, because let's say, again, let's make something up. If I just draw a random vector, how am I going to turn that into, in terms of i's and j's? It depends how long the vector is, but I'm just going to take my i's and then take however many j's I need. I'm doing this very approximately. So it's like, oh, I had 4 i's here, and this is 5 j's. So therefore this vector is 4i plus 5j. Something like that. Keep in mind that it doesn't have to be a whole number, so I just forced it to be 4 and 5 by how I drew it, but maybe it's 4.5, or maybe it's 2.7 or anything like that. So it doesn't have to be whole numbers, because obviously not every vector, depending on how long it is, will divide cleanly into a whole number width and a whole number height. Okay, and that's it. That's I and j. Key thing is this: never forget that I is literally just this vector 1, 0. J is literally just this vector 0, 1. Okay, so a bit more manipulation then. So now A is a vector and it's 3i minus 4j, and B is a vector and it's 2i plus 7j. I'm actually, just so we have some visuals, I'm going to just draw these for a moment. So A is 3i, so that's 1, 2, 3 to the right, minus 4j. So remember, j is that way, so if it's minus 4, it goes in the other direction. Okay, so therefore this is my A. Oh, I should have used a different colour. This is my A. Okay, roughly speaking, that's A. And you get the idea with B. 2 to the right, 7 up, and then draw the line. That's what your vector B would look like. Okay, but we don't need to know that to answer the question, though it's good to be able to have the visual in your head. So we're going to halve that A. We're going to make it half as long. How do we do that? We can just manipulate it algebraically. So I'm going to say half of A, I'm answering this first one. That's the same as a half of 3i minus 4j. Now, what you can do is you can almost treat I and j as if they were just like any other variables in algebra. Now that's, again, you can't take that for granted. I mean, that would have had to have been proven at some point, but it turns out that yes, you can. And that's by virtue of the fact that we showed previously that if you multiply a vector by a scalar, it's just multiplying every element by that number. So you can just treat them like variables. So all I'm going to do now in here is multiply the inside by a half. So I get 3 over 2i minus 4 over 2j equals 3 over 2i minus 2j. And that's it. That's the answer. You just halve all the coefficients. So that was A, part A done. Okay, part B, we're doing A plus B. So that's 3i minus 4j plus 2i plus 7j. So treat I and j as if they were variables, collect the terms, so you get 5i, 3 plus 2, and 7 minus 4 is 3. 5i plus 3j. That's B done. Okay, and then C, let's not do it now actually, because there's a few more examples to look at, but hopefully you get the idea. You'd multiply A by 3, you'd get 9 minus 12, you'd multiply B by minus 2, and then add that on to your previous 3A calculation, and you'd get a final answer. Okay, it seems I anticipated this example already, so draw a diagram to represent the vector minus 3i plus j. Quite simple. A starting point, I is going to the right, so minus I is going to the left, and I've got 3 of them. So there we go, that's minus 3i. And then plus j is there, and therefore the vector is a vector sort of going up and to the left. And there it is. Write this as a column vector. Easy peasy. It's this, minus 3, 1. Okay. What you'll probably find is, personally, I don't like writing vectors in terms of I and j very often, because, as is usually the case, it takes longer to write. so it's easier to just write the shorter version. So when you do your working, a lot of the time it's fine to just work in terms of column vectors, and you don't have to do stuff with i's and j's. But if you're asked to express your answer in terms of I and j, then you always need to convert back again. You'll get used to the idea, but you should treat these completely interchangeably. Whenever you see a vector in terms of I and j, you should also be able to just in your head see that as this column vector here, and just be aware if there's no coefficient, it's just a 1, right? And also, side note, if it was just minus 3i and nothing else, then your j value is going to be 0 because there's no j's, right? And likewise, if it was only j's, then your I value would be a 0. Okay, two examples left. Given that a equals b equals c equals, find the sum of all three. Use column vector notation in your working. Mercifully, they've allowed us to use column vector notation because that is the more efficient way of writing it. So I'm going to straight away write a plus b plus c is equal to, and now let's switch to column. So a is 2i plus 5j, that's 2, 5. B is 12 minus 10. C is minus 3, 9. And then just add up the numbers in each row, the two rows, the x and y. So we've got 2 plus 12 minus 3 is 11, and 5 minus 10 plus 9 is 4. That's it, done. Okay, and finally, here, similar kind of question, a little bit longer. You've been asked to write the answer in terms of I and j. So this is where we take that advice I just gave you a couple slides ago, which is use column vectors to do your working because it's faster. So you can write 2a minus b, and then rather than do all the stuff with the i's and j's, you can immediately convert a into column vector notation. So that's 5, 2. Take away b, which is 3 minus 4. 2 times 5, 2 is 10, 4. And let's keep 3 minus 4 here, just to show our working, one thing at a time. 10 minus 3 is 7. 4 minus minus 4 is 8. That's our answer as a column vector, and now we can convert it back into ij notation. Okay. If you had done all the working in ij notation, you should still get the same answer, of course. This is just faster. So I recommend doing it this way. Cool, all right, so some questions. So I've put 3 questions on this page, and then there's just one more on the next slide. So make sure you do that 4th question as well. Have a go of these. So the first one is just checking you can manipulate the vectors correctly. Then question 6 is kind of coupling that with a little bit of your geometric understanding. 8 is then kind of bringing equations into it a little bit, but hopefully you should be able to answer that if you've understood what we've just talked about. And yeah, have a go at those, and then I'll let you pause and take a look at the final question once you've had a go. So assuming you paused and you've done those, let's take a look at the final question. So this one's asking you to check or to find a certain coefficient given that certain vectors are parallel. So you remember the mathematical definition of parallel is that one vector is a multiple of the other. So you can use your lambda notation for that, your lambda equation. You know, vector A equals lambda B, or whichever two vectors you need to consider, and use that to help answer the question. So write everything down mathematically first, and then play with the information you have. See if you can get the answer. Okay, and then that will do.